Welcome all. So today we will continue with the 2 degree of freedom system analysis. We have seen the process to change a realistic scenario, a realistic beam or any realistic structure into first degree of approximation. Then we saw the same formulation to change the system into 2 degree of freedom system, and we also had a slight taste of changing into a system which has more than 2 degrees of freedom system. After that, we looked into the free vibration case with undamped system. We looked into several examples in which we calculated the frequency of the system, the mode shape of the system, and the response of the system subjected to the different initial conditions. After that, we looked into the translational 2 degrees of freedom system. We looked into the torsional aspects of the 2 degrees of freedom system. So, we will continue with the same formulation. So, now we are looking into coupling coordinates. Okay. So, we are looking into the motion of one coordinate, okay, that affects the motion of the another coordinate. Okay. So, this is called a coupled system. Okay. So, simple example can be vibration of an automobile or a motorcycle. Okay. So, let us say that we are looking into an automobile. Okay. The mass of the system, okay, can be expressed as rotational mass as well as the inertial mass. Okay. And we can model the system supported on 2 springs. Okay. And it has dimension of L1 plus L2 depending upon where the tire touches the ground. Okay. So, this physical system, okay, is broken down into a mathematical formulation. Okay. So, the general equation of coupling. Okay. So, in a general equation of coupling, okay, the non-cross diagonal terms are non-zero. Okay. So, static coupling, when you say the static coupling, it means that we are dealing with equations where the external force is balanced by the stiffness. Okay. So, the term is the stiffness function. Okay. And when we say dynamic coupling, then the inertia comes into picture. Okay. So, then the force is balanced by the stiffness plus the inertia term. Okay. So, if this term is 0, then this becomes a case of static coupling, and if the inertia term is present, then this becomes a case of dynamic coupling. Okay. So, static coupling occurs when the stiffness matrix is not a diagonal matrix. Okay. So, if cross terms are present, okay, then this is called a coupled system. Okay. Similarly, in a dynamic coupling, so this case refers to a situation where the mass matrix is not diagonal. Okay. So, earlier we have seen that our mass matrix was diagonal. Okay. So, in the case where the mass matrix is not diagonal, then we say that this is a case of dynamic coupling. Okay. So, look into the example. Okay. So, how to select the coordinate system? Okay. So, there are 3 systems. Okay. So, there are 3 options for choosing the coordinate system. We can use the center of gravity of the system. Okay. This is the first case. We can use a eccentric point, okay, which is located at a distance from the center of gravity. Okay. So, we can choose this coordinate system in which it is located at a distance e from the CG of the system, or we can use the one of the endpoints in the model. Okay. So, we are free to choose any of this 3 system. Okay. So, we looked into a car case. The distance from the location of 2 springs was L1 plus L2. The springs were defined by K1 and K2, and there was rotational and inertial mass of the system. Okay. So, here this is the representation of our system. Okay. So, spring K2 and spring K1 are there. Okay. And we are assuming that the system is having a motion like this. Okay. So, it is having a translational motion also, okay, and it is having a rotational motion also. Okay. So, the distance from the CG is given by XC, okay, and there is a rotation in the system. Okay. So, there are 2 coordinates, okay, the movement of the CG and the rotation about the CG. Okay. So, the net deflection in the spring is, so this was XC, okay, and it has gone x1. Okay. So, the net deflection is xc minus x1, okay, and similarly here the net deflection is xc plus x2. Okay. So, this is the representation of the stiffness forces in the system, the two stiffness forces in the system, and the effect due to the rotational and translational inertial masses. Okay. So, this is the equation of the motion of the system. Okay. The resistance is given by the inertial mass. Okay. We can write it in this fashion also. Okay. The resistance of the system is given by the inertial component and the resistance is given by the two stiffness component. Okay. So, this is due to the translation of the system. Okay. And similarly, for the rotation of the system, the resistance is given by the rotational mass of the system as well as the rotation occurring in the two springs. Okay. So, this is the equation of motion for the system. Okay. When we are considering the two dependent or the two coupled coordinate system. Okay. So, combining this, okay, we got the equation of motion. Okay. So, in this equation of motion, if we see my masses, okay, the translation and the rotational masses have the off diagonal terms are 0. Okay. So, this is non coupled in dynamic sense. Okay. But in the stiffness, if we see, these terms are non-zero. Okay. So, they are coupled in static sense. Okay. So, this is a case of static coupling, okay, where we have the cross diagonal terms, okay, or the non diagonal terms non-zero. Okay. But here they are 0. So, this is not coupled in a dynamic sense. Okay. So, if we have a case, okay, so if you have a case where K2 L2 equals to K1 L1, okay, so if this is the case, then these two terms will become 0. Okay. Then this will be a case of non coupling in the static sense also. Okay. So, then the whole system is uncoupled in static and dynamic sense. Okay. Now, we change the coordinates. Okay. Earlier we were calculating using the center of gravity. Okay. Now, we have taken one more point, okay, which is a off distance from the center of gravity. Okay. So, we follow the same principle. Okay. We derive the equations, okay, the translation equations and the rotational equations. Okay. And now, if you see, okay, we have a case of static coupling because the non diagonal terms in the stiffness matrix are non-zero, and we have a case of coupling in the mass matrix also, in the inertial matrix also. Okay. So, this is coupled in the dynamic sense also. Okay. So, this is a case of static and dynamic coupling, same system, but depending upon the choice of the coordinate system, now this has become coupled in the dynamic sense also. The earlier part was only coupled in the static sense, meaning the non diagonal terms in the stiffness matrix were non-zero. Okay. Moving ahead, okay. Now, we are choosing the boundary conditions where we are taking the coordinate systems from one of the endpoints. Okay. Same process we are repeating. Okay. So, again we write down the equation of motion in the translation sense and in the rotational sense. Okay. And now, we got the total equation of motion. So, here if you see, the non diagonal terms in both the stiffness and the mass matrix are non-zero. So, it again becomes a case of static and dynamic coupling. Okay. So, we can do one example. Okay. Now, we are putting some numbers to our system. So, the mass is 1800 kg, the values of L1 and L2 are given, the value of K1 and K2 are given, okay, and the value of radius of gyration is given. Okay. We need to calculate the natural frequencies, we need to calculate the principal mode of vibrations, and we need to calculate the equation of motion. Okay. So, we assume that the car moves in the plane of the paper, okay, with small oscillations. Okay. So, here the motion will consist of vertical motion of the car body and the wheel, and the rotational of motion of the body about its mass center, meaning the car is able to move in vertical direction and the car is able to rotate also. Okay. So, rotation will occur and it can move in the vertical direction. Okay. Vertical motion of the car body and the wheel, and the rotational mobility of the body about its mass center. Okay. It means that if this is the mass center, the car can rotate like this. Okay. So, the equation of the motion in considering the degrees of freedom x as vertical motion x and rotational motion as theta. Okay. So, we write down the equation of motion, summation of forces in the vertical direction, okay, summation of motions in the vertical directions due to K1, K2 and the inertial forces. Okay. So, this is summation due to the inertial forces and this is the summation due to the stiffness forces. Okay. So, this is the equation of motion. Okay. Similarly, if we consider the rotation, okay, and if we take the rotation about O. Okay. So, we are considering O out here. Okay. So, we are taking the rotation about O. So, this is the component due to the rotational inertia and the rotational moment, okay, due to the two springs. Okay. So, here we get the equation of motion in the rotational sense. Okay. So, we write them down. Okay. So, here we can see there is dynamic uncoupled. Okay. So, this is dynamically uncoupled and in the static sense it is coupled because the non-diagonal terms are non-zero. Okay. So, this is coupled in the, this is having a static coupling. Okay. So, this is the equation here. Okay. And if we rearrange, we note that the det of this, the determinant of this part has to be 0 in order to get the non-trivial solution. Okay. And J naught, okay, we are writing in terms of mass and rotation of gyration. Okay. So, this is the representation of the rotational mass. Okay. So, after putting the numbers, we got the determinant of the matrix and solving for omega square, we get the two frequencies. Okay. So, the frequency of the system in the translation sense and this is the frequency of the system in the rotational sense. Okay. And after that, if we put the values of omega individually, okay, we will get the value of the mode shape. Okay. So, similarly using the what we learned from earlier sense, okay, we get the mode shape for the first mode and we get the mode shape for the second mode. It simply means that if x is translated 1 unit, okay, then the rotation corresponds to this translation will be in the 1.469 degrees. Okay. And for the second mode, if it is translating by 1 unit, it will rotate in the other direction, okay, of 1 divided by 0.42 units. Okay. So, this is the first mode shape, this is the second mode shape of the system. Okay. So, earlier we were taking 2 degrees of freedom when we were dealing with the 2 degrees of freedom, both the degrees were translation only. Okay. So, now here we have a combination of the translation and the rotational modes. Okay. So, the translation mode will move in the prescribed direction. So, here we have taken the vertical motion. So, it will move in the vertical direction and for the rotation it will rotate in the prescribed direction. Okay. So, these are the two mode shapes. Okay. Similarly, after calculating the mode shape, we calculate the response of the system. Okay. So, the response of the system is given by sine functions multiplied by a amplitude component. Okay. So, this is the solution for the rotational and the translational motion. Okay. And if we put the initial conditions, we can calculate the amplitude constants and the phase difference constant. Okay. So, this we can get from the initial condition if there are no forcing functions or the value of the forcing functions, okay, if the forcing function exists. Okay. So, here in this particular case, we will put the initial conditions and we can calculate the amplitude and the phase shift response. Okay. Now, we extend our analysis to a system where we are having force vibration, but there is no damping in the system. Okay. So, we take the system that we analyzed earlier and we put a forcing function. Okay. So, earlier there was no forcing function, the system was vibrating due to the initial condition. Now, we have a forcing function. Okay. So, this is the free body diagram of the system where we are taking a pseudo inertial forces as per the D'Alembert's principle. Okay. So, here m1 x1, okay, this the degree of freedom is in this direction, okay, the resistance due to this spring is in this particular direction. Okay. So, if we shift this thing, so this becomes plus, okay, and for the second part, okay, for the second part it is in the other direction, so m2 x2, okay, and k2, okay, this guy moves a distance of x1 minus x2, okay. So, this is the equation, okay. So, this is how we can arrange the two equations for the two bodies, okay. What we need to do is that we need to simply cut out this forces, okay, this is equal to, okay, we cut out these two forces and write down the summation of the forces in the vertical direction, okay. So, here For the second body there is no forcing function, so this part is 0. For the first case there is a forcing function f, and in this particular case the forcing function is given by a sine function. Okay. So, here there will be 3 omegas. Okay. There will be omega 1 and omega 2, that will be the frequency of the system, and there will be a third omega, that will be the frequency of the forcing function. Okay. So, we again assume the harmonic motion. Okay. For x1 and x2 we substitute it, okay, and we formulate the equation of the motion. Okay. So, after substitution we get the solution for x1 and x2. Okay. So, this is a chart which is showing the response of the two amplitude x1 and x2 as the frequency. Okay. This is the forcing function with the variation of the forcing function frequency. Okay. Red line is showing x1 and blue line is showing x2. Okay. So, we are taking different cases. Okay. As omega equals to 0, okay, it means that the forcing function can be considered as a static force. Okay. And x1 and x2 have the same amplitude. Okay. So, if they are having the same amplitude, there will be no deformation in K2. Okay. So, what K2 is going to see? K2 is going to see the net deformation due to this two movements. Okay. So, if x1 and x2 are same, there will be no net deformation in K2. Okay. So, what it will happen is that K1 will move x distance here, and again it will move x distance here. Okay. So, the net deflection in K2 will be 0. Okay. When omega is greater than root over K2 M2. Okay. So, then x1 becomes out of phase with x2. Okay. So, then the mode shape is associated with the second natural frequency. Okay. When omega equals to root over K2 M2, okay, then x1 equals to 0, okay, and the equation 6 reduces to this part. Okay. So, we can put these numbers and we can check for different cases. Okay. So, continuing, so we can calculate the values of the different values. Okay. So, here what is happening is that system K1 M1 has no vibration. For this particular case, system K2 M2 act as a vibrational absorber. Okay. So, using this properties, okay, we can design the absorbing system also. Okay. So, if therefore, a vibrational absorber should be designed so that its natural frequency matches the frequency of the external excitation. Okay. So, if the to be or to become a vibration absorber, the natural frequency of this system has to correspond to the natural frequency of the external vibration. So, the natural frequency of the external vibration is omega, and this is the frequency of the absorber. Okay. And since these two are equal, okay, so then this system is acting as a vibration absorber. Okay. Okay. So, the force in the absorber spring at any time is given by this quantity, okay, because this is the displacement quantity and this is the forcing function quantity. Okay. So, when a sinusoidal forcing function is applied to M1 of the main system, it can be ensured that by setting the forcing frequency to this particular value. Okay. The forcing function frequency is set to the vibrational frequency of the absorber system. Okay. So, after adding the spring K2 and mass M2, the M1 mass remains stationary. Why? Because this system is acting like a vibrational absorber. So, this system behaves as a stationary system, even though the external force is applied directly to it. Okay. Though the force is directly acting in this particular system, this will behave as a vibrational absorber. Okay. So, in this condition, all the energy from the applied force is absorbed by mass M2. So, the mass M2, since the frequency of the mass this system is equal to the forcing function frequency, all the energy is absorbed by this particular part. Okay. And this is acting as a vibrational absorber. Okay. Okay. So, now what we have done is that we have started with the free vibration undamped system, we introduced forcing function, okay, and now we are introducing the damping in the system. Okay. So, here we are looking into force vibration of a damped system. Okay. So, again we have a 2 degree of freedom system. Okay. So, here the number of mass is 1, here the number of mass is 1, it can move in the translation direction, it can move in the translation direction. So, the total degree of freedom is 1 out here, is 1 out here, and the sum total becomes 2. So, this is a 2 degree of freedom system. Okay. There is a spring. Okay. So, there are 3 springs present in the system, and now we have introduced the dampers in the system. Okay. After that, what we do is that we cut out this system. Okay. We cut out the 2 portions. Okay. And degree of freedom is x1, and here the degree of freedom is x2. Okay. So, this is the external forcing function, this is the pseudo inertial due to the D'Alembert's principle. Okay. This is the resistance due to the spring K1, this is the resistance due to the damper C1. Okay. So, the resistance in the spring is proportional to the displacement, the resistance in the damper is proportional to the velocity. Okay. So, similarly for this system, x2 is the degree of freedom. So, there will be an inertial component m2x2, okay, the pseudo inertial component. Here the resistance is due to spring K3 and then displacement x2. Here the resistance is due to damper C3 and the velocity x2. Okay. In between, what happens is that this K2, okay, what it is going to say? It is going to see a relative displacement of x1 minus x2, and for C2 there is a relative velocity. Okay. So, this will offer resistance, okay, depending upon the relative motion. Okay. So, here spring K1 is under tension for plus x1, here spring K3 is under compression for plus x2. Okay. So, spring K2 under tension for plus x1 minus x2, it means that if the net value of x2 is more than the x1. Okay. So, if this is quantity is plus, then this will be how the forces will be distributed here. Okay. So, the same system we have broken down into the free body diagram, and from the free body diagram we see what are the forces acting on the system, and these forces we arrange in the equation of motion. Okay. And here we are assuming that forcing function is present as well as the damping is present in the system. Okay. So, we write down in the matrix form. So, in this matrix form, this is the mass matrix, this is the damping matrix, and this is the stiffness matrix, okay, K matrix, or this is also called C matrix. Okay. So, this mass is proportional to the acceleration, this damping is proportional to the relative velocity, and stiffness is proportional to the relative displacement. Okay. So, the displacement is represented as the chosen degree of freedom x1, x2, and there is a forcing function F1 and F2, okay, which is acting at the 2 masses. Okay. Mass matrix, damping matrix and stiffness matrix are all 2 by 2 matrices, okay, whose elements are known as masses, damping coefficient, and the stiffness of the system respectively. Okay. So, they appear to be symmetric. Okay. So, mass matrix transpose of the damping matrix and transpose of the stiffness matrix is equal to their respective counterparts. Okay. So, if we are introducing the external forces to be harmonic, okay, we will see how the responses are play out. Okay. So, this is the steady state solution. Remember, we have 2 parts of the solution, steady state and transient solution, or particular or complementary solution. Okay. So, this is the steady state part. Okay. So, this is, we are assuming that the steady state part mimics the forcing function part, and the transient part we have already seen, where we have put f equals to 0. Okay. So, then we substitute this back into our equations, okay, and we write down the solution in this part. Okay. So, we introduce a impedance matrix, and from there we can directly write down the, if we follow the matrix manipulations, okay, we can write down the solution for the displacements. Okay. So, the inverse of the impedance matrix is also called the frequency response matrix. Okay. So, here we are, instead of representing in terms of time, we are representing in terms of the frequency, the solution. Okay. So, with this we come to the conclusion for 2 degree of a freedom system. In the 2 degree of a freedom system, we started by building upon the basics. We started with a real life system. We choose the appropriate degrees of freedom. First we showed, or we had a revision from the single degree of freedom system analysis. Then we extended the same analogy to a 2 degree of freedom system analysis. We calculated from the free body diagram, we calculated the frequency of the system. From the frequency of the system, we calculated the mode shape of the system, and then we looked into different aspects. First we looked into a system which was having no forcing function and there was no damping in the system. The response of the system was due to the initial conditions. We looked into the behavior of the system. After that, we extended this to the system having forcing functions. From the forcing functions, we then introduced the damping in the system, and after that we looked into a system which is having forcing function as well as damping. So hopefully from this analysis you should be able to calculate the response of a 2 degree of a freedom system. I encourage you to do the examples presented out here and see if the solution matches. Start with doing the frequencies, then look into the mode shapes, and after you are having a confidence of those two things, you calculate the response of the system due to the given forcing function. Thank you. Good luck.